Hello, thank you for joining us today. I'm Karen Novak, Water Innovation Manager for Innovise and Autodesk Company. I'm a civil and environmental engineer with experience working in the water sector, and today I will talk about drainage and the impact of urbanization and climate change. What I'd like you to take away from this session is this: include surface water management early on in the design phase of your project. Let's start with climate change. It rained a lot last month. In fact, October 2023 was wettest month on record since daily rainfall measurements began in the mid-1800s. However, it isn't necessarily that we're having more rain, it's the pattern has changed. We're experiencing more intense downpours, which are almost subtropical. The Met Office researchers are predicting that these extreme rainfall events could become 4 times more frequent in the UK than they were in the 1980s, and that depends on your location. They predict that it'll be up to 10 times more in parts of Scotland and 3 times more in the southeast, which is drier. And this is using their 100-year climate model. The National Infrastructure Committee also published a report last month. They recommend that we take steps now to address surface water flooding. There are over 3 million homes that are at risk of damage due to heavy rain. And of those, there's 325,000 properties in England that are classified as high risk of surface water flooding. And the Commission's study into this risk found that without any action, climate change and urbanization could put an additional 230,000 properties at risk by 2055. So flood risk is real. And currently, if you're an insurer, the expectation is that you'll have about 100,000 homes damaged each year. Urbanization contributes to surface water management problems, and when you lose green space to paving or impermeable surfaces, there are implications for urban planning because the stormwater becomes a problem. This is a map of SW5, a London postcode, and it was taken from the Environment Agency website, and it shows where surface water flooding can be expected in blue, and that's most streets. London has lost a significant amount of surface area to paved front gardens used for parking. So grassy areas are now concrete. And you're probably familiar with the SIWAM study that estimated that the total area of paving in front gardens across London is now about 32 square kilometers, or 22 times the size of Hyde Park. So this is putting strain on our current drainage systems, the traditional drainage. So we need to rethink water. It's a valuable resource. For too long, we've tried to get it away from buildings as quickly as possible through piped drainage networks. So normally, if it rains heavily during storm, water will sink into the ground. But in areas where you have roads, tarmac driveways, large pave areas, it runs down the street and into gutters. With traditional drainage, we treat water as its problem or waste product, and we try to make it disappear using drains and pipes to take it to the nearest water course where it's discharged. During heavy rain, not only do we overload these pipe networks, which can result in situations like the manhole overflowing, this presents not only a risk to property, but also to human health, since this water can be mixed with sewage in combined systems like they have in most cities. There also can be an impact at the other end on the river and stream where you get a surge condition created, and that leads to localized flooding there as well. So when we mention SUDs, and I'm sure you've heard about them, what are we talking about? SUDs is Sustainable Urban Drainage Systems, and they're a way to reduce surface water flooding. It's about creating space for the water to sink back into the ground near to where it would fall naturally. So it's about treating the problem upstream rather than having to deal with it downstream. It's all about runoff reduction, slowing the flow, and water quality improvements, as well as amenity and biodiversity enhancements. SUDS features play a role in the gray to green transition or nature-based solutions. And here are some photos showing swales, rain gardens, ponds, and I'm sure you've seen these in your daily life. When we talk about SUDS, we mentioned the 4 pillars, and those are the 4 bullet points on the slide. Water quantity, taking stormwater out of the drainage network and putting it back in the ground. Water quality, using natural filtration to take pollutants out of the water instead of creating urban runoff. Biodiversity, that's creating green spaces for nature. SUDS can also help fulfill some of the requirements for biodiversity net gain on a site if it's designed properly. And finally, amenity. It looks nice and it makes for better neighborhoods. So our product for drainage design is info drainage. This is the upgrade from micro drainage. Info drainage has more functionality, and it's integrated with Civil 3D so that changes in one are reflected in the other, and it shares the same parts mapping. So we've been investing in R&D and working on this product to improve its accuracy. And that's because SUDS design isn't always easy to model, particularly when you combine SUDS features together to create a system and then use them in combination with pipe drainage. So, for example, we'll consider the swale. It looks simple, but there's a lot going on. And what most drainage software will do is simply take the water, pretend it's a pipe, send it downstream and to storage, and then drain it via an outflow. And that's an oversimplification of a complex hydraulic process. Some of the processes are listed on the bullets. And with the basic swale, you've got multiple interactions going on. You have the water flowing down the slope in the trench. You have water infiltrating the ground. You have water in horizontally flowing through the gravel below, and also vertically into the gravel layer. And you also have the pipe with perforations at the bottom. So we know that the hydraulic response of SUDS in blue is quite different from the hydraulic response of pipe system in red. And you could see how it reduces the peak, it delays creates a delay and runoff reduction, and all of this happens together at the same time. So the changes are coming from upstream and more gradually, and that's because SUDS are spatial, not just in one location. So when we think about a swale, we need to think about the delay, the infiltration, and its conveyance and storage abilities. So if you're using an oversimplification, quite often the gray solutions will win out over the green ones in a model. But with info drainage, which was built specifically for SUDS design from the outset and not as an afterthought, you can replicate how it actually behaves and see what benefits that your SUDS features will actually deliver. And here's an example of what you can model when you put some of the features together. And this is just a nice way to see how a bioretention basin and a swale work in combination. So when you have the rain filling up the bioretention basin, over time, it'll slow the flow, pipe it down to a swale, and stop any surface water flooding. And this is also a good way to test different storms and to see how your SUDS features will react and perform. So we did a real world example. We did some measurements. We wanted to see how info drainage performed. So the red is actual flow, and the yellow is what we modeled in info drainage. And it's actually quite a close fit. And it's much better than the gray dotted line, which was the old way of modeling SUDS. Okay, I'd like to talk a little bit about a customer application where info drainage was used. And this project is interesting because it used a new AI-based tool called the Machine Learning Deluge tool. And that allows engineers and designers to produce a flood map very quickly and accurately by simply applying water all over the site surface. So we trained info drainage on many algorithms, over 10,000 traditional simulations. So that's able to identify patterns between ground models and resulting flood map. And then it can present the user with some flood hotspots like it has in this image. And these can be the best locations usually for SUDS features like ponds, swales, or rain gardens. And this also allows you to save some money on earthworks as well. So it gives you really fast site analysis just through the Deluge tool. It also allows you to try a variety of different iterations. So you can move things around in more real time, make changes, and get instant feedback on your flood map, and understand the impact of your SUDS features, and change the design to get improvements. So this is about optimizing in your design stage. However, in this customer example, the deluge tool was actually used after the site was developed, and we're seeing areas where problems occurred. You might look at it and think, well, that doesn't really look like that's from, it doesn't really look like it's from rainfall on a surface. There's something else that has happened here. And it's true. The construction company in Austin had been called back to the site. It's a school, and it had been flooding during heavy rainfall events. They wanted to collect data fast, so they used drones to collect accurate surface information, and they brought that data into Civil 3D and then into info drainage, and they ran the deluge tool, which gave them the heat map of low areas and surface drainage patterns. So the entire data collection process was reduced from an estimate of 3 weeks down to 1 day. And finding the surface drainage issue after the data was run through the deluge tool and info drainage took under an hour. They overlaid the information onto their as-built drawings to see exactly where the ponding is occurring. And what they found was that their design was fine. Drains were performing properly and flow areas were grading properly. But they found that there were pockets of heavy clay in areas that had expanded and contracted due to weather changes. And these created voids underneath some concrete walkways, and that's what was causing the flooding. So by using these tools, they were able to avoid some expensive and unnecessary drainage expansions. Instead, they used data about the behavior of the water on the site to prioritize a few concrete walkway replacements and backfilling some of these voids with sand. So using info drainage for this process saved them 3 weeks and thousands of dollars in addressing surface water drainage issues compared to what would have happened with traditional methods. So what's next? Well, I hope you have some ideas on how to prepare for Schedule 3 of the Flood and Water Management Act, and think about how SUDS in the design stage can help you with surface water management. Schedule 3 has yet to be implemented in England. Wales and Scotland have gone ahead. In the autumn statement, which was last week, the government indicated that it is minded to adopt Schedule 3, but they did not provide a time frame. The National Infrastructure Committee strongly recommended that it's implemented in 2024. And that's in order to reduce localized flooding and to limit the impacts of growing development. So let's get ready because it's going to be here soon. I've put an image of the SUDS manual. This is quite a large document, and it's currently being updated again. And if anybody needs an abbreviated copy, we do have some, where one of my colleagues has taken the entire manual and condensed it down from 90 pages to far fewer. And also, the other thing that's coming is biodiversity net gain, which I mentioned earlier. We're not sure of the timing on that as well. That has also been pushed into 2024. But it will work in combination with SUDS if you landscape properly and create some spaces for nature. So thank you for joining us today, and please feel free to send through any questions and we will get back to you.